x over 2 and then call that x, and then you have the half number form. It's really the same thing. Okay, so quick comment before we begin. Last time we did something like this. I don't know if you guys remember. And we were supposed to be graphing where the, I think I wrote down where x is less than 0 or something like that?
Yeah.
Right, so x is supposed to be less than 0, which means this, the whole right side of this thing shouldn't have existed. Right? X is positive over here. Someone was reading through their notes and realized, oh, Professor, you made a mistake. Yes, it was an error. I guess you can change that to y less than 0, and then the thing will be correct. So make sure you change that in your notes. I think, was it you who told me?
Yeah.
Yeah, what was your name?
Yufeng.
Yufeng? What's your last name?
Li.
Yufeng Li. Okay, I'll tell you what, Yufeng, since you went and read over your notes carefully, I'll give you 4 extra quiz points for pointing out the error.
That takes care of that.
Just wanted to mention that. So yeah, guys, read over your notes and notice I make a mistake. There might be something in it for you if you let me know.
Oh, you spelled mantra wrong on your syllabus.
Nah, not that. Not mistakes. I'm not an English person. Go on. Okay, so today we're actually going to move on to 10.3, the dot product. You'll also notice that on your quizzes, I give bonus problems at the end where I actually asked you about multiplying vectors. There was a dot and a cross, like an x product thing. We're going to talk about that now. And that's actually going to be typical. So in general, if I give you a quiz or a test, this is not true for the final, but on all other in-class quizzes or tests, what I'll do, I'll always include bonus problems on those quizzes and tests. And what those are are questions on the sections that I haven't taught yet. So I sort of want I want to encourage you to read ahead and sort of, pick out the important points from the chapters we haven't covered yet and sort of know the basic formulas there before I even cover them. I want to encourage that, so what I'm going to do is I always put bonus problems on the next section that I'm about to teach. And that'll always be included on a quiz or a test. So, yeah. So we spoke yesterday about adding vectors, subtracting vectors, pretty intuitive definitions. Now let's talk about finding the product of two vectors. So, someone who hasn't done calc203 before, tell me if you're to hazard a guess how you'd multiply two vectors, right? How do you define that? Right, let's say I have a vector a1, b1. How do you define multiplication?
Well, to take a random guess, I might multiply the corresponding components with each other, so a1 by b1, a2 by b2, add the result, and view it as a scalar.
You would add the result?
Add the results. Put an addition sign there, yes.
That's how you do it?
No, I guess the intuitive thing is to FOIL it. Like a1 times b1 plus a1 times b2 plus a2 times b1 and then a2 b2.
And what would that result would also be a scalar?
Yeah.
Like, how would it look if you were doing that definition?
I would just do that and not add them. I don't know.
I would think most people would try like do that.
Yeah, that's
Like multiply corresponding components, right? So we know when we're adding two vectors, you add the corresponding components. If you subtract the corresponding components. Why not multiply the corresponding components? Is this a good definition of a product?
Yeah.
As good as any you might seem, right? Well, for our purposes, it's actually not a very good way to define a product. There are cases, and I guess it's mostly the math majors that have to worry about this, where you would define a product that way, but for our purposes, it's not very useful, and it has all sorts of weird consequences that come along with it. So for example, notice that if I take these two vectors, right, multiply them according to this definition, what would you get?
0.
You get the 0 vector, right? So in other words, I have two non-zero things, I multiply them and I get 0. It's sort of weird. It's not really a property that we're used to when we're dealing with the real number system. So there are things like that, and there are other things like, you know, when you rotate things using linear transformations, this definition of multiplication sort of messes things up. So that's actually not the way we're going to define multiplication. We're going to define it more the way with the addition that was mentioned before, and that is called the dot product. And we define it this way because it's very useful and it doesn't introduce any unwanted consequences. So let A be vectors. Here's the definition that I'm giving. The dot product it's called dot because they literally denote it with a dot. A dot B. One thing you're going to learn about mathematicians, they're very creative when it comes to making names, right? The dot product A dot B is defined by, so let me, it's actually the sum. So if I look, if we're, and of course, this actually generalizes to larger dimensions. So if my A was something a lot bigger, A1, A2, all the way to AN, and B is the same size, B1, B2, all the way up to BN, then A dot B, A1, B1 plus A2, B2. Right. So this is a very important definition. It's one of the ways we're going to define a product. This product is called the dot product of two vectors, and it's denoted by putting a dot in between them. So on the quiz where I asked you, if A is A1, A2, A3, and B is B1, B2, B3, what is the dot product? It would have been A1, B1 plus A2, B2 plus A3, B3.
So it's not a vector?
It's not a vector. So also on the quiz I asked you, what kind of quantity is it, right? The answer would be scalar. It's a very important idea. The dot product is actually a scalar. And in some textbooks it's even called the scalar product. Because of that reason, it's actually a scalar. It has certain properties that you can, they're not very difficult to prove, you just sort of use the definition and follow your nose. But there are definitions you should be aware of. Properties, right? Some algebraic properties, right? So let's say A and C are vectors, and C is a scalar. Then the following are true. If you take a vector dot product with itself, you actually get the magnitude of that vector squared. And again, just do the definition with A1, A2, blah, 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 and you will realize that you actually have that formula, right? The dot product is commutative, so it actually doesn't matter which one you take first. You will get the same scalar as a result. It also has the distributive property, so A dot B plus C is equal to A dot B plus A dot C. It also has a distributive property for scalars, so A product B, C And number 5, which at this point is sort of obvious, the 0 dot product with A is equal to 0. After this, we have a very important theorem. You can actually define the dot product in terms of the angle between two vectors. And it can be given by this formula. I'm not really going to show you the proof, but I can sort of show you the idea of the proof. So you have two vectors here, here, this is A, this is B, this is the angle between them. Here you can do the, you can actually do the subtraction. So what we can do is call this vector A minus B. And if I think of this as a triangle with these side lengths, then the law of cosines is actually how we can actually prove this formula. Right? The law of cosines will actually tell you that. The left side you can realize is A, B, dot product with A minus B by this formula. And then what you do is you FOIL, you expand, collect everything to one side, you can simplify, and you'll end up with that. Right? That's sort of the idea. Yeah. Formula. And there's a nice angle here, pi over 2. Now if theta is equal to pi over 2, A dot B would be equal to what?
0.
Cosine of pi over 2. And that is 0. Right, but what's pi over 2? That's 90 degrees. That is if A and B are perpendicular, then the dot product is 0, the 0 scale. Your book uses this word, orthogonal. You might see that when you're reading. Orthogonal just means perpendicular, but it means it in a higher dimension. Right? So if you're in 2D, you say it's perpendicular. If you're in 3D or 4D or 5D, you say it's orthogonal. It just means perpendicular. Fancy name for perpendicular. Right? But this is a very important rule here. Right? Your dot product is 0 if A and B are perpendicular. So your A dot B is actually a scalar quantity, and there's a particular scalar that gives us a very special situation. If it happens to be 0, you know that the two vectors in the product are perpendicular. Right? So that's pretty cool. Yes?
So like when you're given an angle and it turns out to be 0, it's a scalar there too? Because
A dot B is always a scalar. So you can try that. Another example. Okay, so in this example, what's A dot B?
First one? 6 over
3
first.
2.
Well, we know that A dot B is equal to A B
Cosine theta.
sine theta. So that's just going to be magnitude of A we know is 2, magnitude of B we know is 3. This is cosine of pi over 4.
1 over 2, so 6 over
That's 2 times 3 times radical 2 over 2. The 2's cancel, and you have 3 radical 2. What's the angle between the vectors?
Can the angle be negative?
No, make it a positive one. I don't. Why would you make it negative?
Can we do it in terms of like inverse cosine, or do you want a simplified answer?
Let's as simple as possible. Tell me how to begin.
Okay, well on one side you want to just do the multiplication of like in terms of 1 times 1 plus
Yeah.
0.
Okay, so let's look at A dot B. That is actually 1 times 1
Plus 0
plus 0
minus 6.
plus minus 6. So that's minus 5, right?
Mm-hmm.
Yeah.
Now that we know is equal to,
The magnitude of A, which is root
Well, I mean,
14.
let me write that out nicer. Since A dot B is equal to A B cosine theta, we have the sulfur theta in the beginning. It's just going to be cosine inverse of A dot B divided by the magnitude of A, magnitude of B. Right? And then now we just plug these guys in. Because your theta is going to be equal to the cosine inverse of
Negative 5.
Negative 5.
minus 5. Hopefully you know how to
Root
compute
5, root 14. That's
that.
what I
Magnitudes were?
Root 5 and root 14.
Okay, so this one's root 14. Remember, it's the radical of this square plus that square plus that square. This radical of 14. And then this is radical of 5. Which is
70.
Hmm?
Root 70. The bottom.
Oh, okay, you can do that. Which I mean, you can cancel root 5 into this and sort of think of it as 5 over 14. You can plug that in your calculator. That's not something you should know off the top of your head. Right. In a test or something, I'd make it nice, like it's an angle that you should actually know. But how do you show that these two vectors are orthogonal? Just take their dot product. 1, 3, 5, dot product with minus 5, 0, 1 is equal to minus 5 plus 0 plus 5 equals 0. So this is one of the reasons why we like to define the product in this way. It doesn't really cause any inconsistencies mathematically, but then it has this really nice property. You can tell when something's orthogonal, perpendicular, just by checking its dot product is 0. And by the time we get to 10.5, you'll realize why that is so useful. We're often going to want to know when two vectors are perpendicular. Anyone has a guess at this one?
So I guess you have 0 equals, if your second vector is B1, B2, then 0 equals A1, B1 plus A2 times B2. That's what it tells you.
Okay, so how do you figure out B1 and B2? As it turns out, there are tons of ways you can actually write the answer. Can anyone give me one possible answer?
So,
Can it be A1 equals 0 and B2 equals 0, then you get
No, I asked for a non-zero vector.
But we can have one component of each be 0. No. I mean, if it's just on the x-axis, it's not a non-zero or a zero vector.
Maybe you could try B1 equals negative B2 and B2 equals B1 equals negative A2 and B1 equals B2. I'm sorry.
I think what he wants, he's trying to say is something like, this vector could work.
Yeah.
Yeah.
It could, right? Because then if you take A1, A2, dot product with minus A2, A1, that would give you minus A1, A2 plus A1, A2. Right? You'll always get 0 no matter what A1 and A2 are, right? And it doesn't even matter which one you put the negative on. I could have put the negative here. That would still work, right? I could have I could have even do reciprocals, right? I could have just make B1 equals to 1, then solve for B2, and I could get it that way as well, right? So the idea is any answer you come up with will be parallel to this vector or its negative, right? But you can start out by just choosing something, right? Sometimes that's going to be what you have to do to solve a problem, right? If anything can work, just pick a number and run with it, right? Because you're dealing with vectors here. And for vectors, sometimes just being parallel is good enough, right? You can scale a vector however you want in many cases, right? There are many cases where the magnitude won't matter, right? So I could have also said, say B1 equals 1, right? I forced this to happen, right? Just because, right? So that would mean that A1 plus A2 B2 equals 0, but that would just mean that B2 is equal to minus A1 over A2, right? Which I can divide by A2 because it's not 0, right? And so then that would mean the vector I'm looking at is 1 comma minus A1 over A2, right? But then of course that is parallel, right? If this is actually parallel to, I can actually multiply that vector by A2, which is a scalar. And then I get that vector. Or I'll get something for that vector. So here I just said, find a vector that's orthogonal. I don't care what size it is, so you can actually just choose one component and then figure out the other one. Little tricks like that are going to come in handy when we're finding equations of lines and planes. Sometimes you don't care about the magnitude of a vector or what point it goes through. You just care about, does it get the job done? So that's one way. But yeah, this or this are pretty much the most aesthetic answers, I would probably say. They'll always be orthogonal because this will always give you 0. And any other answer you can come up with will be parallel to those. Right? So they're really nice ones. Let's talk about projections. Also something that's going to be really important. By projections, I mean the following. Let's say I have two vectors meeting, B and A. Now what I want to do is I want to perpendicularly project the vector B onto A. Right? Let's say I just, like shine a light down at a right angle, and I want to project that vector here. Okay. And so this vector just boom projected down at a right angle to get that vector. Right? So this original vector is vector A. This vector here is called And again, later on you'll see why knowing something like this is going to come in handy, right? Being able to project one vector onto another one. But if you do that and you get the vector, you call it the vector projection. Magnitude of the vector projection is called the scalar projection. So if you project it and you find this vector and then you find the magnitude of that vector, you call it the scalar projection. Let's talk about notation. Vector projection of B onto A is written this way. Project B and little a is down here. This is the vector projection of B on top of A. Right? And the scalar projection of B onto A is called the component of B onto A, and it's abbreviated thusly. So that's the notation. So if you see someone asking for this or that, they're talking about the vector projection, and this is talking about the scalar projection. And it turns out we can actually find, armed with the dot product, we can actually find formulas for these guys. Let's start with this scalar projection. So let me give you a hint as to how we're going to get to the formula. Consider the angle between the two vectors. Now what can you tell me? I don't know if it's orthogonal. I mean, it's might not be to scale.
Magnitude of B cosine theta.
Exactly. Think of this, I'm doing the scalar projection, so we're thinking in terms of magnitudes here. Think of this as the magnitude of B, right? And I want to actually find the magnitude of the base, right? Now if I put a theta in here, this is just magnitude of B cosine theta, right? This means that the component of B onto A is going to be the magnitude of B cosine theta, right? Now, let's say you can't figure out what the angle between the two vectors are. You don't even know the angle between the two vectors, or you don't even want to bother finding the angle between the two vectors. You can actually rewrite this by doing a little convenient algebra, multiply by magnitude of A over magnitude of A. Right? Now what that gives you is A, B, cosine theta over the magnitude of A, which is actually just the dot product. So if you want the scalar projection of B onto A, just take dot product of 2 divided by the magnitude of A. Okay, so with that idea in mind, can someone tell me how to find the vector projection? Right? right, let's say now I don't actually care about the magnitude, I literally want to find the vector that's projected here. And now I actually know what its magnitude is. I can find its magnitude. So how would I actually find the vector?
Why, by a unit vector in the direction of A?
Right, we scale it by that, right? So notice that the projection of B onto A is parallel to A. Right? So all I'm going to do is just take the vector A, but I want to scale it to have that size. So what I do is, so we just need to scale A to have the magnitude of the component. Now, was this in the homework, scaling vectors to be of any length?
They asked for a unit vector that's.
They asked for unit vectors. They never asked you to scale something? Like create a vector parallel to this that has length 5. They just
No.
give you a random.
No.
I thought that would be in the homework. Okay. This is how you'd actually do it. First, you create the unit vector in the direction of A. You know that has length 1. And then you're just going to multiply by the component to make it the length of the component. Right? So, first, take the unit vector, which is just A divided by its magnitude. So that has length 1. And it's actually parallel to A. But I don't want it to have length 1. I want it to have the particular length of this guy. Okay? So going to take that magnitude and then I'm going to multiply it, which by the way, this is a scalar. And I'm going to multiply it by the vector this. I'm pretty sure in the homework you're going to actually use these two guys to figure out certain distance formulas, right? So if you're finding like the distance between a point and a plane and things like that, you're actually using these ideas. And finding distances is obviously pretty important, right? So the projection, both the vector and the scalar projection are very useful for the
So the question is the opposite. The projection of B on A is just going to be the opposite.
If it's from A projecting onto B, yeah, you just switch them. So you have the magnitude of B in here and then B there. Okay, example. Yes. doing that, there's just one more thing I want to mention. Another use of the dot product is in terms of physics. If your force is given by a vector, and your distance is given by some displacement vector, then you can actually find the work done by moving a point with this force along that vector. So, this case, the and again, the picture behind that is you can think of like your object being pulled by this force along that vector, and then you can use the components. You can use the magnitude of f cosine theta to find the magnitude with which it's pulled, and then you can rewrite that in terms of dot products, just like we did before, and you can actually get this formula. The proof of that isn't that difficult. That would leave us to our last example. Okay, let's begin. How do we find the scalar projection?
First we need the distance vector, or the displacement vector.
For this?
Mm-hmm. Oh,
Oh,
Find the dot product.
oh, the projection.
Is this A dot B over the magnitude of A,
Oh, you're doing that.
which is just 3 plus 2 over Root 6. Root 6. Root 10. 5 over radical 10. What is the vector projection?
Dot product over magnitudes.
Yeah, I think some of you think I was talking about the force example. That was afterwards. So then this is actually going to be 5, was it? 5 over 10 times A, which is just a half times the vector A, which was 3 zeros. All right, so if I project this vector onto that one, the magnitude of the vector will be that, and the actual vector will be that. And how do you do the force one?
First, you have to find the vector of the point.
Okay, how do you find D?
So you subtract 1 minus 0, 1 minus 0, 4 minus 1, and that gives you the vector. Then you take the dot product. And it should be
So that
12.
would just be 1 plus 2 plus 9.
12.
The work done would be 12. But of course, if you're given units, you'll know what units to use. Okay, so the important things we learned today. Dot product. We learned the definition. We know what's special, what kind of quantity is a dot product?
Scalar.
Scalar. Is there any special scalar that we know of? Yeah. The perpendicular one. How do we know two vectors are perpendicular? Dot product has to be 0. We also learned about the scalar projection, which has that formula, and the vector projection, which has this formula. These are all pretty important, and we'll be using them pretty soon. The homework for 10.3 is due next class. So that's